There's a couple of really nice ones out here. I really like 2 and I really like 4. 3 is okay. 1's a little boring. It's just kind of computational, but we could try it. Maybe we'll just do it together. So instead of giving, the class an opportunity, we'll just kind of do question 1 and we'll see if we can come up with a solution together. I like that idea. Let's try that. All right. So by the time I've kind of written everything out, we will be at 3:10. We can probably get started. So let's start by looking at question 1. Okay, and question 1 says, we've got this map from Z cross Z into Q, and we know that it's a group homomorphism. I mean, that's kind of always, right? We'll always assume that that's true. We're not just working with kind of arbitrary functions in this class. And we're told that phi to 5 is something, 2/3. And we're told that phi of 3/4 is equal to 1/2, and the question is, I guess this is A. So the question is, what is phi of 0.7? Right? Okay, so generally this question would be quite difficult, right? Knowing something about 2.5 and knowing something about 3.4, as a general rule, it will be impossible to infer information about any other point from those unless what? Unless it's basically some linear combination of these two things, right? In fact, notice that we can look at Z, the direct product of Z and Z is kind of being, almost like a vector space. In that if you think about 2.5, usually we write vectors as columns, but if you think about them as like vectors, then, okay, if we know something about 2.5, we know something about 3.4, and this map has to be additive, right? So that's almost linear. Then the best that we can do is we can say anything about any linear combination of these two vectors. And so the question is, can I write 0.7 as a linear combination of 2.5 and 3.4, right? In fact, actually, this map is quote unquote linear, right? So note, maybe that's kind of worth pointing out here. I imagine most of you have probably not played with the idea of vector spaces over Z. Normally, when we talk about vector spaces, we take it over R or C. If you've taken 240 or 247, maybe over other fields. But let's say note, right? If n is any integer, then phi of n dot, or basically here, let me write it like this. So I take phi of AB and I add it to itself n times. Okay, we don't actually need this for the problem, but I think that this is just kind of a nice, cool thing to think about. So that's phi times n AB, right? And so we're kind of thinking, and if we want to write it another way, we could write, we could put the n inside. So we're kind of thinking about this as a vector, and I can't take a scalar multiple by any real number. I'm not allowed to do that, right? I can't, say add AB to itself 3/2 of the time. Like that's not possible. So whatever this n is, that n has to be an integer. But because this is a homomorphism, I can split it up like this. Right? And we've seen this sort of thing in the past. And look, that, I kind of added these things n times. So I get n phi of AB. And if we look at which equation, so if I look at this thing here, right? And I look at this thing here, that does almost look like, linearity or the scalar part. Like I can pull that scalar multiple out. So again, that scalar can't be any real number like we would normally think about in terms of, in terms of linear algebra, but it looks as though I can take that integer out of the equation. So that's kind of interesting. And then of course it's also additive, right? So also I know that phi of AB plus CD, this is just what it means to be a homomorphism, right? That's going to be AB plus CD. So it looks linear as well. So it looks like it respects addition and scalar multiplication as long as that scalar is an integer, right? So basically, we could solve this problem. This problem, again, imagine that we gave this to you as a linear algebra problem, right? You're given a linear transformation, you're told what the vector 2, 5 maps to, and you're told what the vector 3, 4 maps to. And then I say, okay, well, can you tell me what 0, 7 maps to? The question is, can you write 0, 7 as a linear combination of the other two vectors? So question, can we write 0, 7 as and let's maybe say here, integer linear combination. What were my two vectors again? 2, 5 and 3, 4. Okay, so yes or no, can I do it? Does anyone just see what the answer is? Can I write 0, 7 as an integer linear combination of 2, 5 and 3, 4? Anyone brave enough to do this by inspection? No? So yeah, exactly. Yeah, 3 times the first thing and 2 times the second thing. And if I subtract those, yeah, exactly, I get 0, 7, right? So yes, we would get that 0, 7 is equal to 3 times 2, 5 minus 2 times 3, 4, right? So in that first component, we both get 6s, so they cancel out to give us 7. In the second component, we get 15 minus 8, and that's equal to 7. So perfect. And so what this tells us is that phi of 0, 7 is 3 times phi of 2, 5 minus 2 times phi of 3, 4. And we know what these numbers are. So 2, 5 was 2/3 and 3/4 was a half. Well, that's kind of convenient. It's almost as if it was made to be true. So that looks like it's going to give us 2 minus 1. So that's just 1, like that. Right? And so this is kind of a common thing here. I think that a couple of times people have seen us use this idea that you know, you can pretend that the integers are your scalars, right? And this generally will be true of any abelian group, right? That's kind of worth noting. If you have a homomorphism of abelian groups, it preserves integer scalar multiplication. So maybe let me kind of put that on the side here as a comment, and you should try and convince yourself that it's true. Okay, so comment, if G and H are abelian, okay, and abelian here is important. So if G and H are abelian and phi maps G to H is a homomorphism, okay, then it's linear as long as the scalar multiples are integers. With Z as scalars, right? So what I mean by that is if G1 and G2 are in G and N is Z, then we have phi N G1 plus G2 is equal to N phi G1 plus phi G2. And again, we understand here that when I write this NG1, what I mean is G1 added to itself n times, right? But that's what that means in the real numbers too. So, and frankly, in a vector space, as long as it's an integer, right? That's what I mean by that. Same thing over here, right? This is phi of G1 plus phi of Gn n times. Okay, so that's kind of a cool thing that I think is definitely worth keeping in mind. This kind of comes from a more advanced concept. If any of you are interested in taking more abstract algebra, basically what I'm using here is the fact that every abelian group is a Z module, okay? So you can kind of write that fact down somewhere. Maybe I'll write that here. So if you kind of want to look up more about this, every abelian group is a Z module. Okay, so that's really what's going on there. Okay. Now that's not important. I think it is kind of worth remembering this fact about homomorphisms, but don't worry about what the hell is a Z module? Who knows? Okay, and let's try and see if we can do B together as a class as well, and then we'll actually dive into some of the fun stuff. So we've got to map Z4 plus Z7 into Z28. Okay, we know that phi 13 of 13 is equal to 5. Find the value which maps to 7, or find a value. Okay, so let's do the same sort of thing. On the other side of things, let's look at the codomain right now so that we're working in Z28. Again, the idea is that if I only know something about phi 13, I can't say things in general, like I have no idea what's going to happen. That being said, 5 is actually a generator for Z28, right? So every single element of Z28 is some multiple of 5. So my question to you is, what multiple of 5? In fact, maybe give me the smallest multiple of 5. What is the smallest multiple of 5 such that you get 7 out, mod 28? Okay, this is just straightforward, like Math 102, modular arithmetic. If you add 5 to itself, how many times you have to do that to get something which is congruent to 7 mod 28? Anyone? Exactly. Yeah, perfect. Right. So we note that 7 times 5 is congruent to 7 mod 28. Okay, so what does that win us? Well, it wins us the following. So I know then that if phi of 13 is equal to 5, if I multiply everything by 7, that will give me 7 on the right-hand side, right? Then 7 times phi of 13 is equal to 7 times 5, but mod 28 is equal to 7. Now, as I said about kind of integer scalars, I'm going to be able to go and take that 7 inside, right? So I'm going to get phi of 7 times 13. And again, this means 13 added to itself 7 times. But in fact, everything is integers on the left-hand side. So you can really just multiply it in. And so what is this thing in Z4 mod Z7? And where is my book? Okay, what is 7 times 13? Oh, come on. You all know this, right? So it's going to be 7 comma 21. 7 mod 4 is 3. 21 mod 7 is 0. Right? Just like that. Easy peasy. Not too hard. Okay. So We're going to do question 2 next. I'm going to give you a second to try it. Question 2. This is a really nice one. And in fact, question 2 is really going to help us out for question 4. And I might actually skip over 3 so that we can kind of really see that these two things are related. So we've got this homomorphism, phi maps Z to Z, Z cross Z onto, what did we say, Z? Yeah. And the way that it works is it's going to take a pair and it's going to map it to their difference like that. Okay. So we need to do 2 things. So 1, show phi is in fact a homomorphism. And again, it's a map between abelian groups. There's a sense in which we can look at this and we'd be like, yes, this is clearly linear, right? So there's a sense in which I would almost say this is obviously homomorphism, but it's worthwhile kind of going through the motions and double checking. And then, part 2, find the kernel of this map. And then I guess part 3 is this map surjective? Okay, all 3 are great questions. So why don't we try this out? I'm going to give you, none of these are very hard. Most of it is just like straight up apply the definition, check if it's a homomorphism, find the kernel. For surjectivity, I guess you have to be a little bit more creative, but if you think about it, there's like, it's immediately obvious what the answer is. So I'm going to give us about 3 to 4 minutes here. Let's see what we can do. And again, if you get stuck, don't hesitate to ask me a question in the chat, and I'll answer you in the chat. Okay, so let's give this 3 minutes here to see what we can do. Thank you, Harvin. Yeah, absolutely. I was muted. Okay, so if you're ever given homomorphism and asked to, show it's a homomorphism, those are freebies, right? Those are always freebies. If you're asked to construct a homomorphism, that's a different story, right? Like those questions are usually really, really nasty. So when we're given freebies, we really are happy. And what do we need to check? We just need to check that this thing respects the group structures on both sides. And again, the group structure on both sides is basically addition. On the left-hand side, it's component-wise addition. So let's say, let A1, B1, A2, B2 be elements of Z plus Z, right? And if we act phi on their sum, I'm not gonna lie, this one's kind of boring because we just have to, grind it out. Okay, so here I've used what the group structure is, right, on the direct product. Now I'm gonna apply the definition of the homomorphism. So that's gonna give me A1 plus A2 minus B1 plus B2. And we can split that to be A1 minus B1 plus A2 minus B2. And yep, that's exactly what we want. Phi of A1, B1 plus phi of A2, B2, right? Okay, great. So problem 2 is find the kernel. Does anyone have an answer for this? Like, what did you get? This one's really, really nice. What is the kernel of this thing? Or even like, if you don't want to write it in the chat, like, do you have a description of this thing? Like, what is another word which describes this kernel? A minus A, yeah, okay, so A minus A being equal to 0, A, right, great, Harvin, exactly. And what do we call that thing? You know what that thing's called in ZZ? Or really, if I give you a set and then we look at S squared, right, so S cross S, and we look at all the elements of the form, little s comma little s, does anyone know what that thing is called? No? If you were to graph it, so let's say I give you R cross R, and I said, you know, graph the set. Okay, interesting. So that's true. It's reflexive in the sense that if you're using it to generate a relation on R, then that is the reflexive condition. But yeah, think about it like this. So if you draw R across R, and I ask you to graph x comma x for all x, what do you get? Right? What you get is called the diagonal, right? And you can see why it's called the diagonal, because the graph that it makes is basically the line y equals x, right? It's basically the graph of the line y equals x. And that thing is what we call the diagonal. Right? And that probably makes sense. And that's not just true in R cross R or in Z cross Z. If you're given any two sets, S cross S, or sorry, any set, S cross S, and you look at the elements where both tuples are the exact same thing, that thing is called the diagonal. And the crazy thing, the really kind of crazy thing is that as you start to do more math, it's not necessarily, it doesn't happen everywhere, but as you start to do more math, you start to see people will study a space by looking at its diagonal. It's very, very interesting. So for example, if you go and you do topology, you can characterize compactness by looking at the compactness of the diagonal. Yeah, it's weird the number of places where you can determine things about a space by looking at properties of its diagonal. It's kind of interesting. But so in this case, the kernel is precisely the diagonal, right? Okay, is this map surjective? Right, so I'm going to say fix, some k in Z. And I want to see if I can find something which maps to this k. What thing should I choose in Z plus Z that maps to this? And there's a bunch of things, right? Like we clearly see that this kernel is not trivial, right? This kernel is huge. So what is something that might map to this? Maybe choose the easiest thing that you can think of. Right? Okay. So what I would choose, kind of the natural and evident thing, again, let's think about what the homomorphism looks like, right? So we've got some element k and z, and we know that phi of AB is equal to A minus B, and I want that to be equal to K. So all I need to do is choose A and B so that they are equal to K, and there's a billion things I could choose, right? I could choose K, K minus 1 and -1, or K plus 1 and 1, something like that. To my mind, the easiest thing that I could possibly choose would be K0, right? So far and away, that's probably the easiest thing. And yeah, right, like we're done. This map is surjective. So phi is surjective. Okay, now in particular, now the question doesn't ask us this, but we can say one more thing, because we know we have a surjective map. We know exactly what its kernel is. So by the first isomorphism theorem, right, just again, this isn't part of the question, but as kind of this nice aside, right? So if I take ZO plus Z and I quotient out by the diagonal, ooh, you know what? Let me leave that for a second. So I'm going to quotient out by something, and that's going to be isomorphic to just Z. Now, I kind of want, I could just write this as the kernel of phi. But can someone tell me, when you look at that kernel of phi, is it obviously generated by an element? Like, is it cyclic? And if it is it generated by some obvious element in Z plus Z? Does anyone see it? I'd say, or note that kernel of phi is what? Can anyone tell me what the kernel of phi is generated by? Like what, here's a hint, it is cyclic. What is the generator for it? Okay, so if this is seeming hard now, we're going to be in a lot of trouble when we get to question 4. So this is generated by, yeah, no, Harvin, exactly. It's generated by 1, 1, right? Exactly. Everything looks like some product of 1, 1s, right? Exactly. Yeah, so you nailed it. What is that isomorphic to? Does anyone see? It's cyclic. What is the order of 1, 1 in Z plus Z? Like, what is this isomorphic to as a group? We said it's cyclic. What is it? There's a unique cyclic group of every, countable order. So what is this? What must this be isomorphic to? Yeah, exactly. It's isomorphic to Z. Right? In fact, if we wanted to, let's just kind of do this as an aside. If I wanted to define the isomorphism from, you know what, again, here, let me, instead of writing that like this, let me write it as this thing. AA, or maybe let me write it as NN, right? NN, where N is in Z. And I wanted to map this to Z. Like, how would you define the isomorphism if you really wanted to do it? Like, what would NN map to? Not a trick question. Not certain? Maybe? Just map it to N, right? This map clearly is surjective. It's also clearly injective. Or in fact, the inverse is very, very clear, right? Take N and Z and map it to the element of the diagonal NN. This map is evidently an isomorphism. And so, yeah, we get that this kernel is the same thing as the infinite cyclic group generated by 1, 1, which is in turn isomorphic to Z. So the other ways that we could write this is we could write this as Z plus Z mod 1, 1 is isomorphic to Z. Or, and here's a nice thing, Z plus Z mod Z is isomorphic to Z, right? But again, keep in mind here, when I write this, I'm not saying that Z is a subgroup of Z plus Z, right? Because it's not. They're just incompatible. But what I'm saying is this thing that I'm dividing by is isomorphic to a subgroup of Z plus Z, right? So isomorphic. And we do this sort of stuff all the time in mathematics. Right? That's the point of isomorphisms, is isomorphisms say, hey, these things are basically the same. And then once we know that they're isomorphic and they're basically the same, we just interchange their notation because, again, as groups, they are the same thing. So if you see this Z plus Z divided by Z, you might be like, well, how is that possible? You know, the thing in the numerator are two tuples, right? They're pairs. And the thing in the denominator doesn't even live in that space. We're saying it's not that it's not that Z lives in Z plus Z, it's that something isomorphic to Z lives in Z plus Z, right? So when we write that, that's the sort of thing that we're doing. And again, it looks like there's some sort of nice cancellation here, right? If you think of the plus sign as kind of being more multiplication, you get this cancellation and you get Z out. Okay, so I think that's really, really nice. Okay, so now I want to jump to 4. Okay, so I want to go straight to 4. And we'll come back to 3, but if we have time. But I want to jump to 4, and it says, you can see there's something very similar here. So it says, determine the order of Z plus Z mod 2, 2. Is this group cyclic? Determine the order of Z plus Z mod 2, 2. Okay, is this group cyclic? Okay, now I'm going to give us a second to do this, but we have to be a little bit careful here, okay? Because the group generated by 2,2, right? What is this thing? So this is just all the like, again, it basically just looks like all the integer multiples of 2,2, right? It looks like 2n, where n is in z, right? That's also isomorphic to z, right? This is an infinite cyclic group. Okay, however, z plus z mod 2,2 is not isomorphic to z. Okay, I'm just going to tell you that now. It's not z. So even though in this case, the thing that we've quotiented by is isomorphic to z, the quotient itself is not z. Okay, so we have to be a little bit careful about that. So this question says, first of all, determine the order and then determine whether the group is cyclic. Let's give that a shot. I want to try and give you a little hint here. Let me think. Without just giving it away, if we did that, we said, what's the kernel? Oh, it could do that. That's nice. That's nice. That's nice. Okay. Okay. So as a hint for this, this is what I want us to do. Okay. This is a big hint, big hint. So let's consider the map. Let's call it phi because I'm not very inventive. Okay. No, this isn't going to give me, this isn't going to give me the kernel that I want. Let's do this. Okay, does that make sense? Does everyone understand what this map does? So again, in the first component, so now I want to map to Z plus Z2. And in the first component, we're going to do the same thing that we just did, right? We're going to take this difference between A and B. We already know that that's a homomorphism. And then in the second component, the only thing that I want to do is I want to just take the equivalence class of B in Z2, right? So keep in mind that's Z plus Z2, right? Z cross Z2. And you know, you don't have to do this in order to do this question. If you're like, how would I have ever come up with that map? Don't worry about it. It's actually possible to brute force this. So if you don't want to use my hint here, you can brute force this and it's totally fine and you can get an answer that way. But I think that this map gives you a very elegant solution to this problem, okay? So let's spend 5 minutes on this one because I think that this one's a little bit trickier. But let's spend 5 minutes with this one and see if we can come up with an answer to it. Okay, so yeah, consider this map. What might we want to do with that map? Maybe we'd want to look at its kernel, for example, and see, you know, what can we learn about its kernel, for example. Okay, so give that a shot. Like I said, 5 minutes. Let's see where we get. Okay, let's give this a shot. It's been about 5 minutes now. And if the hint helped you, I hope that the hint helped you. If the hint helped you, it makes things very easy, very, very quick. And again, you could do this by brute force. I think Ali might have done it by brute force. You can check out his video if you kind of want to see how you would do it. If you just kind of want to do it from first principles, for example, if you didn't see that this was the right homomorphism to use. And this homomorphism is hard. Like it's not at all obvious that this is the right thing to do. And so brute force is a completely and totally valid way of doing it, right? But in light of the fact that I'm pretty sure Ali did it the straightforward way, I want to kind of offer this alternative perspective that I think is really, really nice. And one of the things that you might remember is when we were first talking about normal subgroups, I said, you know, first of all, you're normal if and only if you are the kernel of a map. And so the great thing is that when you're looking at quotients, if you're trying to determine what the quotient is, if you can find a homomorphism such that the thing that you're quotienting by is the kernel, then you're in money. You can pretty much figure out exactly what the thing that you're doing that you're quotienting by is isomorphic to immediately, right? Because you just apply the first isomorphism theorem. Okay, so my claim here is that this map is surjective and its kernel is exactly the thing that we're looking at, right? It's exactly the cyclic subgroup generated by the element 2, 2. So let's check that. Let's find out. So 1, I claim that this is surjective. So this is surjective. Okay, and it's very similar to what we just did in the problem above, except now we have the second component, but the second component can only be 0 or 1, right? Because it's got to be in Z2. So those are the only things that we can do. So this is surjective. Let's just check. Let's break it into 2 cases. So case 1 is that we have the map, we have the element K and the equivalence class of 0. And that one's pretty straightforward, right? So note phi of K0 is going to be K minus 0 and the equivalence class of 0. And that's exactly, that's it, right? That's what we wanted. So boom, no problem. Case 2, so let's still use K in the first element, but let's use 1 in the second element. So case 2, so let's look at K1 and let's see if we can find something which maps to this. And of course there, you do exactly what I kind of said, you know, when we were doing the last problem. I said there's lots of things in terms of surjectivity. There's lots of things which map to the element that you want, but I need to make sure that whatever I, you know, put in the second component is odd. So I need to make sure that my second number is odd so that its equivalence class mod 2 is equal to 1. To me, the easiest thing there is probably to do something like K minus 1, or maybe K plus 1. K plus 1 comma 1. So that will give me K minus 1, K plus 1 minus 1, and then the equivalence class of 1. And yeah, that works out. That's exactly what we wanted, right? That's K and the equivalence class of 1, right? So this map is certainly surjective. I don't think that's too bad. 2, what's the kernel? This is a fun one. I really like this. So the kernel of this map, right? So again, this is going to be the set of all AB such that phi of AB, which is A minus B and the equivalence class of B, is equal to 0 and the equivalence class of 0, right? Because that's what the identity element is in Z plus Z2, right? That's the identity element. So if we look at the first component here, AB has to be equal to 0. That's the exact same thing that we had last time, right? In question 2. So we know that A is going to have to be equal to B. But the second thing that we notice here is that the equivalence class of B has to be equal to 0. So our kernel becomes the following. So we get AB where A is equal to B and the equivalence class of B is equal to 0, i.e. B must be even. 2K for some K. Right? And if we want to write that more succinctly, we could say, oh, well, those are just therefore, right? Because again, A has to be equal to B, B has to be even. So it's this thing for all K and Z. And that is exactly the infinite cyclic subgroup generated by 2, 2, right? That is exactly what that is. So by the first isomorphism theorem, Z plus Z mod the subgroup generated by 2, 2 is isomorphic to Z plus Z2. Okay, now we can answer our questions upstairs immediately. What is the order of this group? How many elements are in Z cross Z2? Just, it's not a trick question. Somebody tell me. Oh, come on, you guys know this. This is clearly has infinite order. Is it cyclic? This is the important question, right? Yeah. All right, is that cyclic? All right, I'm going to leave that one maybe for you to decide to figure out if that group is cyclic. But one thing that you might want to consider is its cardinality is the same as Z, right? So if it's cyclic, it must be isomorphic to Z. And, you know, if you want, you can say for the sake of contradiction, suppose that Z plus Z2 is isomorphic to Z. Well, what's wrong with that? What kind of immediately breaks? Maybe think about the orders of elements and convince yourself that those two things can't be equal. And this actually brings up another really cool, really interesting thing that happens in more advanced algebra. So is Z plus Z2 isomorphic to Z? This term is clearly the problem. Right? And the interesting thing here is this is called torsion. So this is Z2. The presence of this Z2 here is called a torsion element of our group. And it's called torsion because there's some number which can basically turn that thing into zero, right? We know that if you give me any element of Z2, it's either 0 or it's 1. I can multiply it by some integer to turn it into 0. If it's 0, it's already 0. There's nothing that you do. If it's 1, multiply it by 2, now it's 0. So the left-hand side has torsion because I can multiply things in order to get a 0 there. The right-hand side has no torsion, right? If you give me a non-zero element in Z, there's nothing I can multiply it by in order to turn it into 0, right? There's nothing that I can do there. So the left-hand side has torsion, the right-hand side doesn't. So these two things can't be isomorphic because you can show if you have torsion, you know, anything isomorphic to you must have the same amount of torsion. So this is called torsion. Again, you don't need to know that, but it's just kind of this cool and interesting thing that happens. And if you want to study more abstract algebra, those are totally the sorts of things that are going to come up all the time, okay? So Z2 here is called a torsion element. Okay, so there's how we call it. There's how we spell torsion. If you want to look it up, it's called a torsion element. And since Z has no torsion, these can't be isomorphic. That's not how we would say it. Basically, I would say there are finite non-zero, non-identity elements on the left-hand side that have finite order, and there's nothing on the right-hand side that has finite order other than the identity, right? So Z2 is called a torsion element. So there are elements. There are, let's say, non-identity elements in Z plus Z2 with finite order. And that's not possible in Z. Okay, so that's the idea there. That's how that works. Anyway, that's going to take us to 4 o'clock. So that's going to finish us off for today. Our next lecture on Monday is going to be our last lecture. Hurrah. We're going to talk about internal direct products. So up until now, this has kind of been external direct products. On Monday, we're going to talk about internal direct products. It's very similar, but just slightly different. So we'll talk about that on Monday. Other than that, I think we're finished for today. So everyone have a great weekend. If you get a chance, please fill out your course evaluations. Like I said, those are pretty important. So if you've already done it, thank you. And if you haven't done it, please take a second, go fill those things out. And yeah, that's it. I will see you on Monday. Yeah, sure, absolutely, Tala. What's up? Let me pause the recording here. Yep. That did not work. Okay, what's up?